Okay, today we're talking about the inverse of a function. So the inverse, it's the opposite, or we say contrary in position or direction. So if we have a function y equals here, y equals x squared, then the inverse of that function, so the blue is y equals x squared, the inverse, it ends up being a reflection of the function in the line y equals x. So we've been talking about reflections as well as our transformations, and we've reflected over the y-axis, we've reflected over the x-axis, and now there's this sort of imaginary line where y equals x. And if we have any kind of function, like the blue function here is y equals x squared, then if I were to reflect that line over this line, y equals x, that would create the red line. And that reflection has a name, and it's called the inverse of the function. So here's another example here. If we have one function like this, if I were to do a reflection over this line, it would create the inverse down here. If I had a straight line here, that would reflect over and create the inverse function down there. And we can go from there. You can have kind of a squiggly line, that could reflect, and so on. And you could have a transformed line. Suppose we're here, it's interesting. Suppose we're here at 0, 2. This thing gets reflected. This point down here, as it turns out, ends up being 2, 0. And we can take advantage of that. We know that if we have, 0, 2, and that, kind of got reflected down to 2, 0, we know that we've been doing all of this work with points. We haven't just been doing random sketching. We're going to use points to do this. We say to ourselves, well, how can we figure out the inverse, mechanically? And the good news is that it's very, very simple. We just take our points, x and y, and we just basically flip them. And we basically, instead of being 0, 2, our new point is 2, 0. And that's going to give us the point. So it's actually very straightforward. So that's occurring here. This point here, we're up at 0, 1. Now we're over here at 1, 0. And, you could do the same thing here. You could pick any point here along and flip it. Try this one here. That's negative 1, 0. So that means I should be at 0, negative 1 down here, which I am. So to plot the inverse of a function, here it is here. Simply switch the x and y coordinates. And then for convention, we're going to solve for y. So I'll show you how we do this with an equation. So suppose we're asked to find the inverse of y equals x squared. So I have my basic function, y equals x squared. What I do is I actually just flip the x and y mechanically. So here's my x and here's my y. I just put the x over there and I put the y over there. And I have x, so instead of having sort of y equals x squared, now I have x equals y squared. So that's actually the inverse. That's it. You're actually done technically. However, like I said before, for convention, we don't really have equations ever solved for x. They're always solved for y. So for convention, we have to do a little more work and just solve it for a y. Just write it back in that y form like we normally do. So the inverse part is actually just one step. It's just doing this flip, and then we have it. From there, it's just mechanics, just putting it back into our normal structure. So obviously it's pretty straightforward. I have y squared. I don't want that. I want y. So I have to square root both sides. I square root the right side. I square root the left-hand side. The square root of y squared becomes y, and I'm left with plus or minus the square root of x, which is a square root function, which is actually kind of interesting. So if you have a quadratic function, which is y equals x squared, then the inverse is this square root function, y equals plus or minus root x, which we've kind of seen because we have a sense that the squaring thing and the square rooting thing are the inverse of each other. So notation-wise, there's one more thing I want to point out. If we're given a function y equals f of x, we would write the inverse of a function as our notation f negative 1 at x. And I'll show you why I have to do this in a second. So find the inverse function of, we'll just do a straight line for now, y equals 4x plus 8, we'll just keep it simple. So here's my y equals mx plus b, it's very easy, y equals 4x plus 8. I flip the x and the y. So instead of having y equals 4x plus 8, I have x equals 4y plus 8. So that's the flip part. Okay. And that's technically, that's it. That's the inverse. You have it. You've flipped the x and y's. You have the function. That's the inverse. But again, for convention, we don't really ever have functions solved for x. We have them solved for y. So now we just are going to solve this thing for y just because we're used to it in that form. So for that, I'm just going to subtract 8 from both sides. It's pretty easy. Subtract 8. I divide both sides by 4, so I'm left with just y. So I have x divided by 4 and negative 8 divided by 4. X over 4 I'm going to leave. 8 over 4 I know is 2. So now it's a little weird because now it's solved for y, but in our mechanics we have this kind of weird thing. We have y equals this and we have y equals this, which is two different things. So I'm going to replace this y, this here, just with our notation, f negative 1 of x. Because I know, because I did the flip, I know I'm dealing with the inverse. I want to write it as the inverse. I don't want to leave it sitting there as y because it gets confusing. So now it's just a notation issue. I just changed that y into my inverse notation. And I'm going to flip it around. I'm just going to bring this over to the left side and not to the right side because typically we have things written, we always tend to write our things, y equals, not, equals y. So I'll just bring my inverse notation over on this side. And that's it. That's what the function looks like. Okay, so try some of those questions and you're done.